Okay, let's get started. Sorry for the delay. So today we are going to be talking about transformers. Last class we spent a lot of time covering the self-attention mechanism. This class we will first continue the stuff we were doing on the iPad to add in some things that we weren't able to cover last class. Then we'll switch over to these slides and talk at a higher level about the transformer, all of its individual components, and how it's actually used to perform the task of language modeling. We'll also introduce the concept of sequence-to-sequence learning, which is very related to the models that we've discussed up till this point, but has the added feature of an encoder and a decoder, where you essentially have an input sequence and an output sequence that you want your model to produce. So before we start, some stuff, logistics things. So your proposals, we gave you a week extension. Hopefully that is sufficient time for all of the groups who were having issues. There's a quiz 2, due this Friday, so make sure you submit that. Someone asked if TAs could record their Zoom office hours. I don't know, I'll ask the TAs and we'll see if we can record those. I guess some people might have private questions that they want to ask in office hours, so I don't know how we'll deal with those. Maybe we can pause the recording or something, but anyway, the answer to this is maybe. We will discuss and see. Someone asked on the anonymous form, how did we get this grid that was shown in the previous lecture? So this will become more clear once we talk about sequence-to-sequence models for machine translation, which we will briefly do today. But in the case of a machine translation model, you have a source sentence and you have a target sentence, right? The source sentence here is in, I guess, English, and the target sentence is in French. The model gets the entire source sentence as input, right? This is how, if you imagine you want to translate something on Google Translate, you put in an entire sentence in whatever language it is that you have, and the model is asked to produce the entire target side translation, so this whole French sentence here. In a sequence-to-sequence model, the model that's producing the French sentence is called the decoder, the target side thing. Note that the encoder does not have to actually generate any text, right? Because it's given to the model as input, the entire sequence. The decoder, however, can perform attention over the encoder as well as the previous words in the target language that it's produced up till this point. So you can see here the decoder, encoder attention. This is what this grid represents, and you can see that there's some mappings between words that mean the same thing in French and English. So this is a concept of alignment, if you are familiar with machine translation, that the models for machine translation that were used prior to these neural models relied heavily on these alignment models, but attention kind of gets you these things for free, these alignments. So the model is actually learning to perform word level alignment as a function of its training objective, which is just to predict the next French word. So that was what this was showing. Someone asked what's the exact deadline for the final project reports. That is December 16th, aka the last day of final exams or something. All right, any questions on unrelated logistics stuff? Cool. Any YouTube questions? Okay. All right, so what do I do here again? All right, let's switch over to this. So there are a couple of things that I wanted to cover on the iPad, and then we'll kind of go through them again on the slides, but hopefully it'll be more clear if I show you this on in writing as well as with the slides. Last semester that I taught this class, people were super confused with the transformer, which is understandable, like it's a pretty complicated thing, so I'm gonna try and do a little bit better this semester, so we'll see. So let's take our let's take our input that we've been using every class, students opened there. And so last time we talked about these query key value projections, right? Maybe I'll draw those out again just to reinforce. Okay, I think it's green for the keys. One, blue for the queries, and right, and we talked about how to compute these things, right? Just a simple linear layer, multiply this this embedding C1 with a parameter matrix, and then apply some nonlinearity like a tanh or ReLU, and you can get these query key or value embeddings, right? So the next step, what did we do next? So let's say we did this for all of the, well, okay, that was not good. Let's say we did this for all 3 of our words in this sequence. What did we do next? What did we use these query and key vectors for? Right, so given, say, this query, I would compute the dot product. Sorry, let's, oh, see the numbers are messed up here. Wow, this. So given, say, Q3, query vector 3, I would compute the dot product between this and K3, this and K2, this and K1. I would apply the softmax. I would get a distribution over these 3 key vectors. I would then use the distribution that I get to do what? So I have 3 probabilities. Yes, exactly. So I get 3 numbers, maybe 0.3, 0.2, 0.5, and I'm going to just take the linear combination of these. Wow, that's completely not understandable now. But take the linear combination of these value vectors using these probabilities as weights, right? So all of that is clear. All right, let me undo all this stuff. So one thing that we did not talk about is how this kind of model handles the order of the words in the sequence, right? So the way I've described it so far, this model doesn't actually handle the order of the words in the sequence, right? Because the value weighted average is just based on these probabilities. There's no notion of the order of the sequence in that computation anywhere. So in a recurrent neural network, this isn't an issue. Why is that? Exactly. So in a recurrent neural network, remember that we're computing these things one at a time, right? So every single time we compute the next hidden state, we already have a representation of all the words that we've seen, and now we know that this current word is going to be following all of those previous words. In this case, we're not doing that, right? Remember, in this case, we're computing all of these. If you remember, let me use a different color. Let's just say these brown vectors correspond to the attention weighted average of the value vectors. So if we compute all of these in parallel using that matrix product that we saw in the last class, there's no way that the order is being encoded here. We're computing each of these representations separately of each of the other ones, right? So the way that we actually encode word order is quite simple. Okay, let me actually move all of this up. Okay, So in the transformer, what we do is, what color have I not used? Orange. We're going to just add an embedding that corresponds to each position of the sequence. And we're going to add this embedding to the input word embeddings, these C sub 1, C sub 2, C sub 3. These are called position embeddings. And so we can say P sub 1, P sub 2, P sub 3. And these P's, there's a variety of ways we could obtain them. In the original transformer paper, which I think I assigned to you as a reading, but I understand it's pretty complicated to get through that paper. In this paper, they essentially have a fixed, not learned, a fixed function to compute these P sub i's, the position embeddings, which we'll talk about later when we get to the slides. You could also imagine having a separate position embedding matrix, just like we do with our word embeddings, right? So remember, we're learning these C sub i's, the word embeddings, they're all in a matrix and they're getting backpropped into. We can do the same thing with these position embeddings. So we can randomly initialize these position embeddings, say to whatever, and then backprop into them based on our loss function to update the position embeddings. So, for example, if my maximum sequence length, the biggest sequence I can fit into my GPU is 1024, so I can have 1024 tokens in my input, I'm going to have 1024 separate learned position embeddings, one corresponding to each position. So P sub 1 here is always used for the very first position in the sequence. P sub 2 is always used for the second word in the sequence, regardless of whatever input it is. Does that make sense? So there's a difference between learned position embeddings, which is what I just described, where these orange things are backpropped into and learned through the training objective, and fixed position embeddings, which are just set beforehand using some function, and they're not updated at all. They're not part of the model parameters. If you're using a fixed function, there are several important things to consider, which we'll go over when we get to the slides. But essentially, you want it to be, different, obviously, as you increment the position. You want the difference between two positions to be consistent, regardless of what the size of the sequence is. There's a whole bunch of other things that you might want. There's actually, a fairly large body of research now on specifically position embeddings and what kinds of position embeddings are better than others. The easiest thing by far is just to use a learned embedding, just like you would for a word embedding. The downside of that is, of course, that it cannot generalize beyond the maximum sequence length that you've defined, right? So if I have 1024 learned position embeddings and I get a test time of 5,000 word long sequence, I don't have position embeddings to represent the later positions in the sequence. So with a fixed function, this is easier if your function is able to take in arbitrary lengths as input. Okay, any questions? Yes?
Why do we add position embeddings of concatenate?
Oh, that's a good question. You could concatenate them, pass them through a feed-forward layer. You could do any sort of composition that you want. It's simple, I guess, to add. There's no real reason. Any other questions?
Wouldn't the parameter size be dependent on the length of the text position embedding and not just the number of tokens?
So it depends on, so if you're using learned position embeddings, then yes, but it's a very small number of parameters, right? It's just one parameter, or sorry, maybe if your dimensionality is like 500, you add 500 parameters for every sequence position that you increase your maximum sequence length. So it's not like you're adding a huge weight matrix block per position.
But we train these models on Wikipedia text and most people these are very lengthy text.
Well, oh, sorry, I forgot to repeat the question. Sorry, what is the question? Wikipedia text and Wall Street Journal text, he said, are fairly lengthy. So maybe if you train your model with huge sequences, you're actually adding a lot of parameters. Is that your point? But in practice, you actually can't just put like 100,000 token long sequence into the model. Like your GPU memory is not going to be able to handle all of this. We also have to talk about the complexity of the self-attention mechanism, right? It's actually quadratic in the length of the input sequence. So there's many factors limiting how big sequences you can put into your memory. Position embedding parameter size is not one of them. That's a very small fraction of, yeah.
There is also one question from YouTube. Why does any composition is okay for position embedding? Delete it right now as it is.
Okay. Yeah, I don't know how to answer that. I mean, you just need something to inject the information about the positions into the representation that you're feeding into the self-attention mechanism. There are many ways to add parameters to these kinds of models, as we'll see. And so just adding parameters into this very first layer is maybe not a great way to go, especially when you have blocks of different layers that you're stacking on top of each other. So this only happens, by the way, at the very bottom of the network. That's another thing that we'll go over right now. So, okay, we have these, yeah, go ahead.
So I was just wondering if this is a problem only at the decoding stage and not at the encoding, because since we do use the mask and we don't allow the future tokens to affect the attention, like the previous tokens.
So the question is are you referring to the position? So the question is, do you only need to use these position embeddings during decoding time where you can't cheat and look forward in the future versus at encoding time where you have the entire sequence? The answer is no. So if you think about this as an encoder, let's say you have the full sequence, you can attend to every position, you don't need a mask. Even in this case, you have no information about the position of each individual word without actually having these position embeddings injected into the model, into the input embeddings. Does that make sense? So if I don't have this, the attention function itself is not considering order, right? The scores are just a dot product between a query and the key. This is going to be the same regardless of where that key is in the sequence, unless it has some information about the position of the key in the sequence. Yeah.
So does this mean like if you have a decoder and you are using the whatever code is done, you won't be able to decode more than the maximum decode?
Yes, that's correct. So the total sequence length, like input and generated text, cannot exceed the maximum sequence length. So models like, I think GPT-2 or whatever, I believe they use learned position embeddings, but I might be wrong on that. But there are, very frequently used models that use learned position embedding. I think Roberta also might use learned position embedding. So there's a mix. We'll talk about the original formulation. We'll talk about, I mean, we don't need to talk more about the learned position embeddings. They're quite simple. There are also other newer methods that have been proposed, like rotary embeddings was a recent thing. We won't get into too many of those variants, but yeah, you can definitely look them up if you're interested. Okay, so what was I doing next? Oh, yeah. So another thing that the transformer introduces is the concept of multi-head attention. So this is something that we have not covered so far. All of the attention that we've looked at up till this point has been single head attention, meaning we only have one set of queries and keys, and we are only computing one representation at every time step. The intuition behind multi-head attention is, well, if I compute, say, 3 different queries, 3 different keys, 3 different values for each position, potentially each of these heads can learn to look at different linguistic properties of the input. So maybe one head focuses mostly on noun relationships, another head focuses on, I don't know, entities. There are many things that you could imagine each of these heads are doing. So just to draw this out, what the output of a multi-head attention would look like is multiple of these z vectors, and each one comes from a different set of query, key, and value projections. So how do I make this not cluttered? So let's say I'll use this notation, where the subscript represents a position in the sequence and the superscript is the index of the head. So this is the output of the second head. This is the output of the third head. So let's say I have 3 heads. In this case, I'm also going to have 3 query representations. So Q1, 2. And I'm going to have 3 key representations and 3 value representations. And I'm going to do this for every single position in the sequence. So what does this do to my parameter count of the model? If I want to add a new head, what do I need to add as far as a learnable, like trainable parameter into the model? Exactly. So the new parameters in, say, this case, all right, I'll just use black. My new parameters are WQ1, WQ2, WQ3, WK1. I don't know why I'm writing all of these out, and so on. So instead of having just one matrix, which W sub Q, which we saw before, well, that was for our single head, now we just have 3 matrices, 1 for each head. Each of these is going to be randomly initialized and backpropped into with our cross entropy loss. Yes?
Each of the things is a word, and they are the prefixes to that word. Right? Is a representation of a word Q, and P is the prefixes to that word, and then we get a value. So if you're saying that Q1, Q1, P, is it the same word representation in a different?
Yeah, so let's be more clear. Q1 equals F of WQ1, C1. Q2 equals F of WQ, Q2, C1. Q3 equals F of WQ3, C1. So they're all projections of the same input. The only thing that changes is the weight matrix, the W. Also, the second thing you said was the keys are prefixes of the that we've observed up till that point. That's not completely accurate, right? The keys are produced in the exact same way as the queries, with just different weight matrices. So you have K1, K2, K3. The only thing you're changing is the weight matrix that's used. It's just a role of these things in the self-attention equation, right? The query Q1 is used to dot product against all the keys that came before that, up till that point. Yes?
What do you use for that function F?
The question is, what do you use for the function F? I think in the transformatives, it's a ReLU function, which is just take all negative values and set them to 0. Actually, there's a recent paper that I'll mention at the end. It came out like last week that shows that the squared ReLU function, where you just square the output of a ReLU, is a lot better. No one can really explain these things, but we'll talk about that in a bit. Yes? So the question is, we have multiple heads, do they all get the same gradient? The answer is no, because the weight matrices are all different for all of the heads, right? Yeah, but since the weight matrix is different, the attention scores will also be different, right? So if Q1 and Q2 are functions of different weight matrices, they will be different vectors. So the question is, why don't all the heads try and learn the same thing? They are initialized differently, so it might be optimal for the model, if it wants to minimize its loss, to use different heads for different things. I mean, it's hard to explain why head 1 would learn a particular pattern and head 2 would learn a particular pattern. As we'll see later in the semester, these kinds of intuitions are not really meaningful anyway. It's a very nice story, right, to say, oh, well, head 1 focuses on this kind of word and head 2 focuses on this kind of semantic relation, but in practice it's extremely hard to tell what the heads are actually doing. But they are doing, okay, I mean, it's a good question, because there's also work showing you can, after training these things, prune off huge portions of the heads. So you can, for example, prune all but one head in each layer and still maintain a lot of performance. However, it's necessary during training to have all of these heads. So I don't know. We'll talk about all this stuff later on, but in general, there's a lot of stuff people don't know about these models. They empirically work well, but a lot of the decisions that are made in their design are kind of, at least the intuitions that were originally put forward are wrong or misleading, but empirically they work well. So it's still a very new field. All right, any other questions? Yes.
So the final output for all the heads will still be like books, right?
Oh, yeah. So let me go through the final output first. I'll just get rid of these. So let's say, just for space reasons, we'll do it on top of z sub 3. Oh, well, I have these 3 here, so why not just do it on this? So what happens now is that I now have 3 different z's, right? 3 different value-weighted averages, the output of 3 different heads. Now, one of the problems is I need to get a single thing that I can pass through into my softmax layer to predict the next word. So how do I do that? It's in the transformer, pretty straightforward. I will just concatenate all of these things together. So let's say this part is the sub 1. So I make this really big vector. Then I pass this thing through a feed-forward layer to get, sorry, and by feed-forward I mean like linear or fully connected, whatever terminology you want. Let's say linear layer. And I'll get some vector that's kind of composed all of the concatenated things together. And from this I'll predict the next word, which in this case was open. So a lot of the parameters of the transformer are in this linear layer, because this concatenated vector can get quite large as I expand the number of heads. And some of these models are using, actually I think GPT-3 is like 48 or hundreds of heads or something like that. So this vector can be quite large. And if you imagine you want to, say, project that down to a more reasonable dimensionality, you're going to have a very big weight matrix in the feed-forward linear layer, right? So a lot of the parameters of these models comes from this particular thing. Lots of params. Okay. And as a result, a lot of the memory footprint comes from this feed-forward layer as well. Okay, so any questions about this entire process? So the 2 things we've discussed here are, first, position embeddings, so the model knows where each word is in the sequence. Second thing is multi-head attention, so the model can theoretically look at different parts of the sequence, the different parts of the prefix in this case.
But computing the GP, we have got to quickly with the previous term. So we do have some information around the position in dark and light. So the previous term.
So, Okay, let's do a example. The question is, even if we don't have position embeddings, don't these dot products somehow account for the position? So let's take a look at Q3. Let's say I want to compute the attention scores for Q3. What I'm computing is Q3, K3, Q3, K2, Q3, K1, right? I'm computing these three dot products. So K1 is a function of C1, K2 is a function of C2, K3 is a function of C3. Note that K2 is not a function of C1 and C2, right? So it has no knowledge of what came before it in the sequence. It actually has no knowledge of the sequence at all, right? It's just the input word. Similarly, K3, right, is just a function of C3. So you need to add this explicit notion of position in order for that position to be taken into account here. Anyone else?
Yes.
Yes.
A lot.
A lot? All right, great.
Okay, so let's start from the shortest one. How will we predict there?
How will we predict, you mean like,
From students open there.
so you mean the next time step of this?
I guess so. Or like the word there.
So the way you predict a word is by passing this representation that you compute after all of these attention computations, the concatenation, the linear layer. You pass that final vector into the softmax layer, which we've talked about in several classes now, right? So that has its own weight matrix. It projects this black vector into the space of the entire vocabulary, and then we use the cross entropy loss to train this. So that's what's happening to predict open. That's also what's happening to predict there. You just have the next time steps attention vector as input.
Another question is there nonlinearity added while going from concatenated that one single vector over the next?
Yeah. So here, in this linear layer, it's something, okay, let's say this is going to be, I don't know, what's a letter I haven't used before? X maybe. So this vector X is going to be, I don't know what we'll call this, WX maybe, of this concatenated thing here. So yes, there is a nonlinearity. I think in particular, this F here, this new paper says to use the squared ReLU, and it makes things a lot easier to train. Okay, is there more?
Yes.
How many more?
2.
Oh, okay.
Okay, rather than concatenating, why not consider Z1 with 2 with 3 as one test of blob and part with the CNN layer rather than linear layer to reduce the parameters?
Yeah, so the question is, why do we concat and then feed forward? Why don't we use any other composition method, right? You can imagine maybe even putting a RNN over these Z vectors, or even just averaging the Z vectors, or doing something else. The answer to all of these kinds of questions is unsatisfying. This is what the Google researchers who invented the transformer found performed best, and so they used it. I think also it's important to have this weight matrix, this W sub X, because it is such a huge contribution to the overall size of the model. There are papers we'll discuss later on in the semester showing how bigger models are capable of learning more things. And so if you were using some element-wise function, you might not be able to easily scale the model size. All right, last question for now.
That's the last question.
Oh, great.
The question will follow up comment from the same person. How these attention models process tokens, whether the batches are related to blocks of 124 tokens or a different set of streams where the earliest tokens are exited first, and then the person also commented, so I guess it's not really feasible to have it to be a stream, but that means that if S scoring was 2048 tokens, there would be no way for the 1025 token to
Oh, I see.
attend to the 1000.
Okay. Well, thank you for reading that. I think the overall gist of this question was, how do we use a model that has a max sequence length of, say, 1024 to process a much longer sequence of, like, maybe a story's 10,000 words long? The answer is unsatisfying. You have to chunk the story up into chunks of 1024 and process them. There's also interesting stuff we'll talk about later on about like how even if you have a model that has 10,000 words of context, practically speaking, how many of those words does it actually use when predicting the next word? And the answer is not. It's like beyond 2,000 words, it's not really using the previous tokens. So the models are not very satisfying right now in terms of long sequence understanding. All right, so one other thing that I wanted to do is explain how these models are made to be deep. Because right now, we've just been talking about a one-layer transformer, essentially. However, oh, that was cool. However, the most of the models that we'll see in this class are deep transformers, meaning they have multiple layers of this kind of attention block, multi-head attention, before they get to the softmax layer. So let's see how I can do this. Kind of want to preserve all of this stuff. All right. Okay, so for now, let's just ignore the, oh, can I not move this anymore? Right. Oh, no. Okay, great. So for now, let's ignore the multi-head attention, just because this is already pretty cluttered. I'm going to erase all of this stuff. We'll get rid of our multiple heads, all of this stuff. All right, whatever, good enough. So here, at this point, we just immediately went to the softmax layer to predict the next word. What happens, so this whole thing we can call layer 1. And now, instead of going directly to the softmax layer, I'm just going to use these z's as the input to the next layer. So now I'm going to take these z's, I'm going to project them to Q1, K1, B1, so on. Do the exact same thing, get more z's, Z1, 2, this notation is bad. Okay, second layer, Z sub 1. So I get some more vectors here after this attention weighted average. And I can stack, many more blocks. More layers. And then finally, I'll get to a point where I'm satisfied with how big my model is. I'll get these final layer Z's, and from this I will predict, what is I predicting? Books. So if you look at this kind of architecture, you see the position embeddings and the word embeddings are only used once at the very bottom of the network. And then we're just stacking more and more of these attention weighted averages on top of this. And the Z's here, the Z's no longer correspond to an individual word, right? After the first layer, the input doesn't have a one-to-one correspondence with the word at that position, right? This Z sub I at position 3 has information about the entire sequence, students open there. So you can see as you stack these layers, the model is just like contextualizing information from across the entire prefix up till that point. You have multiple heads also, which I haven't drawn here. But yeah, so in the multi-head attention, this is actually the X matrix. That's the result of the concatenation and the feed-forward layer. Maybe I'll write that here. So yeah, this, so then this is X21. Okay, it actually kind of works here. Anyway, so this is how we make these models bigger. We just add more layers. In each layer, you have separate parameters for that layer's multi-head query key value projection matrices. You have parameters for that layer's feed forward, this W sub X, which is responsible for doing the multiple head concatenation into the smaller vector. You only have one softmax layer in this model, right? It goes on the very top layer of the entire transformer. Yeah, so the concept of layer in a transformer is kind of confusing because when I say layer, I really mean a block of computation that it includes all of these query key value projections, the attention weighted average, the concatenation of the multiple heads, the feed forward layer at the end. All of these computations are referred to as one block of the transformer, and you stack these blocks. So it's not really like a layer in a normal neural network sense, yeah.
On the base of query keys and values, they're different for every concept, or
the W sub Q, they're different for each layer. They're the same for every position in the sequence in the same layer. They're shared weights, yes. There's another question? No? Okay. Great. So there are other parts of the transformer block that I have not covered in this iPad thing, but we'll cover them on the slides because they're not as important. I mean, they are important for training the model. They're just annoying to write out of this. So we'll switch over to this slide. Okay. Margena, is this displaying? Oh, there's a delay. Right. Okay, so a couple of things to cover here before we get into the nitty-gritty of the transformer block. The first is sequence-to-sequence learning. So if you read the transformer paper that was assigned, you will notice that it was talking about machine translation, and it was talking about things like encoders and decoders. So here, this is used when you only want to generate like one sequence and you have another sequence as input, like as a prompt, for example. So you have no interest in generating the prompt. You just want to generate the target output. So in machine translation, this is easy to think about, right? You have input in a source language, you want to generate the input in the target language. For, say, question answering, you can also think about your input, your encoder gets a question, and you're interested in generating the answer to the question. For dialogue, right, you might get what someone just said, and your output, what you want to generate, is what your response is, right? So lots of these tasks can be framed as a sequence-to-sequence problem. As we'll see later on with the T5 model, lots of NLP tasks in general can just be reformulated into the sequence-to-sequence setup. But let's say we're looking at machine translation. We're translating from French to English. This is our example. So our goal, we're given the French sentence with these tokens, F sub 1, F sub 2, and our goal is to produce the tokens in the English language that correspond to the translation of that. So we'll talk more about machine translation in a separate lecture by itself, but this is just an example for the general sequence-to-sequence setup. So our goal here is now not to just compute the probability of the English translation. So this P of E, this joint probability, is what we're computing in a language model, right? Now we have a conditional language model. So we want to produce the English sentence conditioned on the French sentence. So this P of E given F. This more generally is called conditional language modeling. And it's exactly the same as what we've seen up till this point. You just add some more things in the chain rule to condition on, right? So if I wanted to produce these English tokens, E sub 1, E sub 2, blah, 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 conditioned on F, the French sentence, the chain rule decomposition is just the probability, the product of the conditional probabilities, where all of these conditional probabilities are additionally conditioned on the entire French sentence, as well as the previous English words in the sentence that you're producing. So just like what we've seen before, you're just conditioning on the French sentence as well. So the traditional sequence-to-sequence setup, you're using two different neural networks to model the French side and the English side. Why might you want to do this? Why not just use the same network and share the parameters? Yeah, so the vocabularies are very different, right? French might have a completely different vocabulary. English may have a different vocabulary. And so the word embeddings are normally not going to be shared among both of these languages. Maybe you want the model to specialize on one language and on French or English. Now, these days we have these unified models that just encode both French and English with the same exact model. We'll talk more about that later on in the semester. But historically, the first instantiation of the sequence-to-sequence models was with separate networks for encoder and decoder. Okay, so in sequence-to-sequence, models were introduced in, I think, 2014, and the first version of them was with recurrent neural networks. So I have this French sentence, which I'm not going to pronounce, so just say it in your head, I guess. And that is encoded by this encoder RNN. So note that here, I'm not predicting any words. I have no softmax layer in my encoder. I'm not interested in producing French words. I only want to produce English words. So I use this RNN. Remember, this is 2014. We are not using attention even here. So this final vector here represents my entire sentence. It's a bottleneck vector. It's not going to be a good representation, but theoretically, at least, it has information about all of these words. Now, I'm going to feed this vector as input to my decoder RNN, which we've seen before. It's just a RNN language model. It's taking these input tokens of the English sentence as input and combining that with the hidden state. And now you see the connection between the encoder and decoder. Remember, in a recurrent neural network, we had that initial hidden state, that H sub 0, which we said we could randomly initialize and learn, or we could just set it to zeros. Here, we initialize it to the last hidden state of the encoder RNN. So now the model has all of the information of the French sentence in the initial hidden state, and the rest of the time it's just predicting English words and updating its hidden state to account for both the French, this vector, as well as the words in the prefix that it's produced up till this point. What's that? Mm-hmm. So the question is, the order of the words in French and English in this example are relatively similar. Is that what you're saying? But in some other examples, it could be completely different. But note that this vector, if it's doing its job, it will include mostly the semantics of the French sentence, like the meaning of the French sentence, and possibly not the exact order of various words in that sentence. And so if you consider this as a representation of the meaning of the French sentence, then this decoder's job is just to produce that meaning in English, reproduce that meaning. I agree in practice, in French to English, there's going to be a lot of this monotonic alignment. Maybe in German, where like I guess in past tense or something, the verb will be at the end. You have these big shifts in the alignment. But still, like these models are relatively decent at handling those if they're trained for a specific language pair.
So is there some sort of mapping between the representation of French that this model learns and is there the representation of English that's being used to decode? Is there some
So the question is there a mapping between these red?
word meaning? Yeah, in other words, how the model works?
Oh, I see. You mean like how is a model trained is what you're asking.
Yeah.
Yeah, so these machine translation models are trained using large parallel data. So for example, in the European Parliament, they produce, as a normal part of the proceedings, like the translations of what's being said in many different languages, like French, English, Spanish, whatever. And these have been aligned, and they've been released as machine translation data sets where I have this French sentence, this is what the English translator said that was equivalent to that, and so on. And this kind of data is used to train these models. So I know the ground truth translation that I want to produce. That's where my loss is coming from. Can we use the same encoder model for different target languages? Yes, there has been work on this kind of thing where I keep this model fixed and then I just have a bunch of different decoders that are specific to each language. We may talk briefly about these things when we discuss the machine translation as a task separately.
You said that these models are basically trained on European Parliament data. So how do we address the bias that comes in because the nature of that language would be formal in nature?
Yeah, so the question is, these machine translation models, if they're trained on this parliamentary data, how do they generalize to other domains like maybe informal chat or something like that? That's a good question. They have data sets that are not from the European Parliament as well. It's just the biggest data sets are generally from there, but they also have like movie subtitle parallel data, so you get other domains that way. There's a lot of work on this kind of like domain shifts in machine translation. So I agree it's an issue and people are studying it, but it's also very hard to get parallel data like this at a big enough scale to train these models. Okay, let's move on. Is there a YouTube thing? Okay, so it's clear that we have an encoder. Its job is not to produce text. And then we have a decoder whose job it actually is to produce text. And when we're training, we've already seen this loss function before. It's exactly the same. The loss is only on the decoder. But we're able to propagate this loss through the encoder by virtue of this connection that we have, right? The hidden state of the encoder, the final hidden state, is connected to the decoder. It's used to initialize the decoder. So when I'm predicting have, I'm backpropping into this decoder hidden state. I'm changing the parameters of the decoder's WH and WE matrices. And that backprop, the partial derivatives go all the way into this encoder. So here you can clearly see the benefit of attention, right? If I only have this one pathway into the encoder that's kind of bottlenecked by this one particular connection, it's going to be very hard for the gradients from far away in the decoder sequence, like over here, 7 time steps into the decoder, it's got to go a long way before it gets into the encoder and influences it, right? We talked about that vanishing gradient problem. So here, attention mechanisms, this is actually the setup for which they were originally developed. I can, instead of just conditioning this prediction of have on this green vector, I can do attention over all of these 4 red vectors in the French language. And maybe this will be more easy to pick up the word-to-word alignments between French and English. So we talked about attention in the context of these language models that are just in a single language. They're just predicting the next word. Here, you can have different types of attention. I can have attention, for if I'm, say, at time step 4, I can have attention over the previous 3 green vectors. That's what we talked about last, or 2 classes ago, whenever we discussed this, right? This is called target side attention. So I'm attending over tokens in the decoder alone, not the encoder. I can also have source side attention. So this is where at time step 4, I'm looking at these 4 encoder representations. I'm not looking at these 3 decoder side representations. So in the transformer, they call this decoder side thing just normal self-attention. And they call, when I'm looking at the encoder's representations, source attention or cross attention. So there are 2 different types of attention in the decoder. In the encoder, in a transformer, I only have self-attention. I'm not going to be looking at the decoder, right? That doesn't make sense. I don't even know what I'm supposed to translate. So the encoder transformer version is just full self-attention, no masking at all, right? Because I have no cheating concept if I already know the entire sequence. It's the decoder that has masked self-attention and cross-attention to condition on these encoder representations. Is that clear? All right. So we will, again, talk about machine translation in its own lecture later on. We're just going to cover all the model stuff first, and then we'll cover the cutting-edge machine translation stuff. But for now, we need to talk more about the transformer, unfortunately. So this is the diagram that you probably saw in the transformer paper. And you were probably like, what is happening in this diagram? So we've talked about a bunch of these concepts already on the iPad. But here, first of all, this left side in the green box is the encoder. So it's getting as input, this input's here, you can just assume is a French sentence. And the decoder is producing the English translation. So let's take a look at some of the components here. We see multi-head attention, first of all, in the encoder. If you look at the corresponding block in the decoder, you can see it's masked, right? So we talked about the idea of the mask. If you're producing these words, you need to have the mask to prevent cheating. In the encoder, we obviously don't have the mask because we have all the information already. Okay, so we'll get to these add and norm things later. What I want to show you is this second block of multi-head attention in the decoder. So you can see that it's actually connecting to the encoder, meaning this is performing cross-attention. It's not doing self-attention on the prefix of the decoder stuff. It's actually looking at all of the Z's or the X's, whatever we were using, from the encoder, the final representations that are produced by the encoder. So I have these 4 vectors from the French tokens here. That's what this is doing attention on. So here, the query, it comes from the decoder side input. The keys and values come from the encoder's final layers. So I project those to key and value, and then I compute my attention weighted average on the encoder side. Does that make sense? Maybe that was confusing. Okay, yes. What are the outputs of this block? Oh, you mean this? So the question is, what are these outputs? So you can think about these outputs are just the prefix of the English translation that I've generated to this point. So during training, right, I have the entire ground truth sequence because my training data contains full French, English language pairs. This is shifted right because we want to include a start token. So the very first time step of this decoder, it shouldn't know the identity of the first word, right? It should just rely on the start token and this cross attention and figure out what the first word to produce is. So the output sequence here is like start token, what was our example? Yeah, so you can see it here. It's the same. Start, the poor don't have any money. Yes, yes. But during training, right, we can do all of this in parallel because we know the entire ground truth translation. And we also talked about how we can do all these computations in parallel in the previous class. so the question is, if the task is language modeling and not machine translation or some sequence-to-sequence task, do we need a decoder? The answer is yes, you always need a decoder. In language modeling, all you have is a decoder. The question should be, do you need an encoder? The answer is, if you don't have a sequence-to-sequence task, no, you don't need an encoder. You can just get away with a complete decoder-only model. So all the stuff we've been talking about before these slides are decoders only. If you're using that terminology, you can call it just a decoder. Note that in machine translation, the decoder additionally has this cross-attention. In the models that we talked about, there was no cross-attention because that didn't even make sense. There was no input sequence other than the prefix.
Yes, we are translating from French to English. Suppose in a large corpus, if the number of words in some language changes, the corpus in English has different size. Will it handle the translation?
So the question is, if the English sentence has more words than the French sentence?
Or in some other language.
Or different?
Yeah, if it is more or less.
Yeah, so even if the English sentence has different number of words than the French sentence, the model is still capable of producing this translation. So the way this works, and we'll talk about this more when we talk about decoding from these models, is generally at test time, I will feed in the input sentence, and I'll feed in to the decoder just the start of sequence token, and I'll ask it to produce one word at a time until it produces what's called an end of sequence token. So once it produces an end of sequence token, I just terminate that decoding process, and I say, this is my translation. There's no restriction that I have to have the exact same number of decoding time steps as I have input tokens in French. So the model can decide to produce as many tokens as it wants before it produces this end of sequence token.
But the same question is, when training is done, isn't that going to be a problem because you're conditioning for based on the lecture?
Yeah, so during training, you don't need to do this one at a time, right? You already know the full target translation, so you can do everything in parallel, but you have to add the end of sequence token during training so that at test time, the model knows it has to produce an end of sequence token when it's done.
So, but if the number of words in the French sentence and English sentence would be 10, it's unlikely, but then if it's French is 10 and English is 20, does the model chop up the English sentences into 10 blocks of 2 each and then transition like that? Or?
No. So the question is, if the French sentence had 10 words and the English sentence had 20 words, does the decoder, is it only able to model like 10-word chunks?
2 words. Because it needs to create those dependencies, like one block to one block.
Yeah, so here, let's say I'm at the decoder. So this is already an example, right? This English sentence is longer than the French sentence. So if you're talking about the cross-attention, at every point here, I'm always only attending over 4 representations from the encoder, right? So at time step 4, I do cross-attention over these same 4 representations. At time step 5, I'm doing cross-attention over these 5 representations. So there's no dependence on the length of the decoder's output. All right, we'll move on and you can ask later. Okay, so these slides are a representation of what's happening in the encoder, and hopefully they kind of make everything that we discussed on the iPad more concrete. They were made by Emma Strubel, who got her PhD at UMass and is now at CMU as an assistant professor. So let's say our encoder, okay, I know this is in French. Let's just assume we're translating English to French now, is Nobel Committee awards Strickland who advanced optics. So this is this sentence that we want to translate. So first, let's say we're at the first layer. So we have our word embeddings, right? The C sub i's. We project these to query, key, and value, right? And so now, if you take the query and the key dot product, this is going to give you that attention distribution for the very first time step, right? Similarly, I can do this for all of the time steps. And so I get these attention distributions one for every time step. So this is where the model should be looking for each of these positions. Note that I didn't have to do any masked self-attention here because I have the entire sequence already. My goal is just to produce good representations of this input sequence. So I have this attention distribution over the 7 words of the sequence. Now I'm going to do the attention weighted average of the value vectors, right? So I'm going to compute these yellow vectors, which are the attention weighted average. And then I have this multiple head thing, right? So everything just gets multiplied by how many ever heads I have. So now I have these 4 attention weighted averages. I'm going to concatenate them, pass them through the feed-forward layer, and that's a feed-forward layer. And now I get the final output of this layer. So as we talked about, we don't just have one layer. We're just going to stack these, and I'm going to have as many of these layers as I want. And then finally, this is going to all just go into the input of the cross attention in the decoder. So the decoder is going to tend over all the final representations of whatever comes out of the encoder. All of these parameters in this model are learned through backpropagation from the decoder's loss function all through the parameters of the encoder. All right. Great. So there are things we talked about like the position embeddings. Those are added at the very first layer. These are residual connections, which are represented by this arrow. This means that when I get the output of a particular block, I'm going to add it to the input of that block and then pass the addition of the input and output onto the next layer. So if we go back to this, and hopefully it doesn't break my computer. So here, at this point, on the iPad, I said, all right, we're going to take these brown representations and just feed them as input to the next layer. In practice, we actually add these brown representations to the original input of this layer. So that's what's going on here. You see this plus. And the addition is, the sum is then moved as input to the next layer. So residual connection is used to improve the gradient flow in a model, give some shortcut to the input of the previous layer. Similarly, there's layer normalization that's used to also improve the gradient flow of the model. We're not going to talk about that here. Okay, so we talked about the feed-forward layer, and then talking about stacking this model to get a deeper and deeper and deeper network. Okay, and we talked about this already. We've talked about the masked self-attention that's used in the decoder to prevent the model from cheating. And we talked about why we don't need masked self-attention in the encoder because we already have the full sequence as input. All right, and the cross-attention. I feel like I should have done these slides sooner. Okay, and then finally we have our softmax. All right, so I'm actually just going to skip this part on position embeddings. We'll talk more about this in a bit, but I guess maybe I'll go over this at least. So intuitively, if I'm not using learned position embeddings, I want some kind of fixed function that's able to handle a huge range of positions and also have the difference between 2 positions be meaningful. So if you think about this binary encoding, you can see that this digit over here in orange, this is only flipping every 8 positions. This green one is flipping every 4 positions, the blue one every 2, the red one every 1. And so if I extended this, I could use this thing to model like a lot of different positions. The transformer is using like intuitively a similar concept, except with not these like binary bits, but rather floating point numbers using a sinusoidal function. So if you visualize the position embeddings of a transformer where each row is the position embedding of a different position, they look something like this. So they have some patterns, they have some relationships, but they're unique for every position in the sequence. As I said, you can use this, you can use learned position embeddings. They each have their own issues. I wanted to finish with the hacks because these are hacks, but they're also very important to make the transformer work. The first thing is the learning rate. So we talked about the learning rate of the, when we were talking about gradient descent, right? This controls the step size, how much in the direction of the negative gradient do we want to go. Transformers are generally trained using this optimizer called Atom, which is doing like per parameter learning rate schedules and so on. You can read more about it. It's kind of outside the scope of this class. But there's also this warm-up concept of the learning rate in transformers, which is super critical to getting them to train properly. So this shows on the x-axis the essentially what batch you're on. So this is batch 0, batch 5,000, and so on. And this shows different learning rate schedules that the authors of the transformer paper had to go through. So essentially you start and the y-axis is the learning rate. So you start your learning rate very, very small. You gradually increase it up till some point linearly, and then it exponentially decays to some number. And so this point at which it switches is important. The exact slope of these things seems to depend on the model size. It is, kind of incredible that they found this particular thing, the learning rate schedule, because if you just train it using a fixed learning rate, it doesn't work at all. So imagine how many things they had to try before they found this particular thing that works. Kind of insane, but Google also has an insane amount of compute resources. So that's one thing that's very important. All of the transformer layers in the libraries that you will be using, they're generally trained using this kind of optimizer. So yeah, you won't have to implement it yourself. Label smoothing is something that came up in a previous class where maybe we don't want the model to put 100% of the probability on the word that it observes during training. So if the training sentence is like, I went to class and took blank, and the training data has notes in it, the way that we've described this, we would put 100% of probability on notes and 0 on everything else. But in label smoothing, I'm going to subtract some probability from the ground truth and evenly distribute it among all the negatives. So the model is penalized for being too overconfident if it's trained with label smoothing. So you can see that here. Like as the confidence increases, the loss is going up because the model shouldn't be 100% confident in notes. There's obviously synonyms and other things that are plausible that could go in there. And finally, I wanted to just briefly mention this very new paper that came out like a week ago. It's called Primer, Searching for Efficient Architectures. So someone asked about this neural architecture search. And so you might be wondering, why do you put the residual connection here and not here? And why are we using 8 heads instead of 2 heads? And why do we have this feed forward and concat instead of some other function? All of this you can only answer with Google tried all these things and they found that this works best. But even Google can't try all possible combinations of things. So neural architecture search is basically automating this process of trying out new architectures. This recent paper looked specifically at transformer architectures. They found that first, adding a convolution on top of the output of these query key and value projections before feeding them to the attention works pretty well. No one can explain that. Also, adding just element-wise squaring after this ReLU function is like the single most important thing that this architecture search found. So it burned like all this CO2 was expended, and finally we found that just squaring one of these layers is super critical. But like no one would have found this before, right? It's not something that you would ever think to do. So it could be a massive benefit if it makes these models much easier to train. And one last thing, sorry, now we're out of time, is I wanted to also just give you a sense of how quickly transformer models have evolved. So OpenAI has released the most prominent transformer language models starting in June 2018 with GPT. It's the first language model they released. It was like 120 million parameters. So parameter count is like all those weight matrices, how many entries are there in those. Trained on 13 gigabytes of data. GPT-2 was not even a year later. They scaled it up to 1.5 billion parameters. They scaled up the amount of data as well. Then GPT-3, the next year, a way bigger model, right? 175 billion parameters, almost 500 gigabytes of training data, so 300 billion tokens, 300 times what they did 2 years ago. And now they're even bigger models, like many companies have internal models that are even bigger. It's not really clear when we'll hit the limit of just like brute force scaling the data and the model size. It seems like hopefully we'll hit it soon and then we can do more intelligent things. But yeah, this is currently the state of NLP. All right, so see you next week. We'll talk more about transformer stuff then.